Hello and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 153, find minimum in rotated sorted array. Before we get into it, two things I want to say. If I sound a little bit different, it's because I'm under the weather, so my voice may sound a little different than normal. Second, you guys know the drill. Please subscribe to the channel, help me grow. It's really good for the channel. Alright. Suppose an array of length n sorted in ascending order is rotated between 1 and n times. For example, the array nums 0, 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 2 if it was rotated 4 times, and 0, 1, 2, 4, 5, 6, 7 if it was rotated 7 times. Notice that rotating an array, a of 0, okay, I'm not going to read all of that. Basically what it's saying is that each rotation shouldn't really be called a rotation. Basically you're just shifting the elements to the right one time. So given the sorted array nums of unique elements, return the minimum element of this array. And you must write an algorithm that runs in big O of log n time. So basically, let's look at an example and figure out what we need to do. So we have this nums here, which is 4, 5, 1, 2. And obviously the minimum value here is 1. And in this other nums, which is 4, 5, 6, 7, 0, 1, 2, the minimum is 0 because that's the smallest number. So on paper, it's really easy, right? Just find the minimum of this array. And if it didn't have to be done in log n time, all we need to do is call the minimum function. But we can't because it tells us we have to do it in log n time. Now, if it hasn't already screamed binary search to you, then I don't know what will, because we have an array that was sorted at one point and we need to write our algorithm in big O of log of n time. The only important thing to notice here is that while the array was at one point sorted, remember in the beginning it's always sorted, but we moved the elements to the right however many times, right? So this array was at one point 1, 2, 3, 4, 5, but we've moved it a few times, so now that it's like 3, 4, 5, 1, 2. But what you'll notice is that no matter how many times you rotate it, part of the array will still be sorted, right? Everything from 1 onwards is sorted, and everything from this 3 up until the 1 is sorted. So this gives us a little bit of a hint as to how we might want to set up our binary search. Because even though the array has been rotated or shifted to the right a few times, it's still going to maintain its sorted property, although there will be a point where obviously there's a drop off because this is where the rotation happened, so there will be an element that's larger and then we go to an element that's smaller. That's how the rotation happens. So basically, identifying those points will help us actually find the minimum because it's going to happen around one of those points, right? When we go from a large element to a small element, we know that that small element has to be that minimum value. So we're basically looking for the point that this drop off happens. Now, there's a few edge cases we need to consider, and I want to get rid of a little bit of this text here to give us more space to think through this problem. So in a second, I'll wipe this all away, and we can think about how to solve this question intuitively. Let's think about how to actually set up the binary search in an intuitive manner. And remember that we need a binary search here because we, first of all, have a sorted array. It may be rotated a few times, but it is still sorted in 2 halves, and we know that we need a log n runtime. And since we have basically a sorted array and we need log n runtime, the only thing that's going to give it to us is a binary search. So let's think about what we want to do here. So as with any binary search, we typically set our left to be 0 and our right to be the length of nums minus 1. So in this case, it's going to be 6 because this array is length 7, minus 1 gives us 6. Now, how do we set up our actual while loop for the binary search? In this case, we're actually returning a value when we find it, which is the minimum of our rotated sorted array, and it's guaranteed to exist in here. So because we're returning a value from our binary search, we can actually use the while left less than or equal to right for our binary search because we're actually returning a value from inside of it. Now let's think about the 3 cases here about where we might actually return a value here. So the first case is, let's say we roll the dice and we end up at this 7 as our midpoint, which is actually the midpoint of this array, so it works out nicely. Now, what we want to do is find the minimum. So if ever we're at a value and its value to the right is actually less than it, and that is where the sorted part ends, which is where our array was originally kind of set up, but we had rotations, right? In no other case is, in a sorted array, its right neighbor actually less than the previous one, right? So when this happens, this indicates that this is where the array was rotated until. And we can see that when we have something like this, where we have a value and its right neighbor is actually less than it, then that right neighbor must be the the minimum in the array. So in this case, we're going to find the midpoint and we're going to check, is the value at the midpoint? So this is case 1, where the midpoint value is actually greater than its neighbor. So nums of mid plus 1. So if this is true, then what we want to do is return that right neighbor. So we're going to return nums of mid plus 1. Okay. Now we could actually have the opposite being true. What if we land on 0 as our midpoint? We want to check the opposite. Here, in this case, we were checking the right neighbor, but it could be the case that we actually end up on the minimum, which, in order to verify it's the minimum, it actually needs to be less than its left neighbor. So we can do the opposite check. So we can check for whether or not nums of mid, whatever the midpoint is, minus 1, is actually greater than our midpoint value. And in this case, that means that our midpoint value is actually the minimum. So we're going to return the minimum, the midpoint value, which is the minimum. The third case is that it's inconclusive, right? So in this example, we actually end up somewhere. So it could be like 4, 5, 6, 7, 0, 1, 2. So let's say that either we ended up somewhere in this bucket, somewhere between 4 and 7, or somewhere between 0 and 1, right? So we ended up in one of these two buckets, right? Maybe we ended up at the 5, maybe we ended up at the 1, who knows? What we want to check here is whether or not our array here is sorted. And this is going to give us a hint. So now let's think about this. Let's say that our left value is actually this, the midpoint value is our 6 here, and our right value is this 2. What we want to do here is we want to check, is our midpoint value actually greater than whatever the number at the right pointer is, 2. And the reason we want to check this is that, look, if this part was the sorted part, then it should be always increasing, right? If it's sorted, then we should expect maybe 6, 7, 8, 9, 10, right? If it's sorted. But the fact that it's actually not sorted, right? It goes from 6, 7, 0, 1, 2, and we indicate this by the fact that 6 is greater than 2, which is the right value here. Because this part isn't sorted, right? Obviously, if it was sorted, then it should always be increasing. But because it's not, we know for sure that somewhere between the 6 and this 2, those indices, right? Because this is our midpoint indice, and this is our right indice. We know that somewhere in here is the minimum. So if we observe that our midpoint value is actually greater than the value at our right index, then we know that somewhere inside of this range is the actual minimum, right? And which is that 0. So in this case, what we want to do, so if our midpoint value is actually greater than nums of right, then what we want to do here is we actually want to move our left pointer to be mid plus 1, right? We already know that 6 isn't the minimum, so we're going to chop it out and we're going to set our left to be this 7, and we're going to continue our search. So our left is going to become mid plus 1. And if this is not true, then our else statement kicks in, which is simply going to set high to be equal to mid minus 1, because that means that we would need to search the other side for that minimum value. So those are your 3 cases here. Hopefully it's not too confusing. If it is, don't worry. Once we go to the code, I'll type everything out and you can verify that it's all going to work. But that's the general gist and how we're going to solve this problem. So now what I want to do is to go to the code editor and we're going to type this up and submit it. All right, I will see you there. We're in the code editor. Let's type this up. Before we get into the binary search, there's actually a few edge cases we can take care of. So let's do that. The first edge case is that there's only one element in the array. If there's only one element, then obviously it must be the minimum, so we can return it. So we're going to say if the length of nums actually equals to 1, then we can just return, sorry, I can't type today. We can just return nums of 0. The other edge case we want is that either the array wasn't sorted or it was sorted to some multiple of its length. So what this means is that it's actually not going to change. If there's 3 elements and it was shifted 3 times, then everything's just going to return to its original position. Same is if it was, length of 3 and you shifted it 6, 9, 12, 15, yada, yada, yada. It doesn't matter. It's just going to return back to its original position. And the way that we can actually identify if the array is still sorted is that if the nums of 0 is actually less than the last element. So basically, if the first element is less than the last element, then that means that it's still sorted in its original position. Because with the rotations, we won't have that sorted property being maintained, but if it's sorted, then this should hold true, and therefore we don't need to actually do anything. We can just return the first element because the array is still sorted. So if nums of 0 is actually less than nums of minus 1, then what we can do is simply return nums of 0. Cool. Now we can actually set up our binary search. So we're going to say left is going to be 0, right is going to be the length of nums minus 1. Now we can say while left less than or equal to right. What we can do now is calculate the midpoint. So we're going to say left plus right, divide by 2. That's going to give us the midpoint. Let's get the midpoint value. So the midpoint value is going to be whatever nums of mid is. And we want to now go through our 3 cases. So let's go through the first one. So we're going to say if the mid val is actually greater than nums of mid plus 1, then we know that our nums of mid plus 1 is actually the minimum. So we're going to say return nums of mid plus 1. Then we're going to go into our other case where the mid val is actually less than its left neighbor. So if nums of mid minus 1 is actually greater than our mid val, then that means the mid val is the actual minimum value. So we can return the mid val here. Otherwise, we have that case where we need to move our left and right pointer up accordingly. So if the mid val is actually greater than nums of right, then we're going to say the left value is going to be mid plus 1. Otherwise, the right value is going to equal to mid minus 1. So I just want to run this, make sure I haven't made any syntax bugs, and we look good. Let's submit this, and we are good to go. So what is the time and space complexity here? Well, obviously it's a binary search, and the problem told us that we had to use this time complexity. So we know that it's going to be big O of log n because it's a binary search. What is the space complexity? Well, we don't use any variables here other than left and right. So this is going to be a constant space allocation. So it's going to be big O of 1 in the space. So that is how you solve the problem. Find minimum in rotated sorted array. This is one of those fun binary search questions. It does come up often in interviews, so it's definitely one to know. And it's generally one of the easier ones because it can be solved by actually returning a value from within the binary search, instead of the harder ones where you actually just have to move the left and right pointer down until you get to some condition and then return one of them as your solution. So this one's definitely one of the easier ones. Anyway, I'm going to stop blabbing here. If you enjoyed the video, please leave a like and a comment. It really helps with the YouTube algorithm. If you want to see more content like this, please subscribe to the channel. I have a whole lot of videos already uploaded, and I plan to make a whole lot more in the future, so stay tuned for that. Otherwise, thank you so much for watching today, and have a great rest of your day.